In this chapter we're going to look at the circle. Mathematically, the circle corresponds to the circle line. It is defined as the set of all points that have the same distance from a given point to the circle center. Try to label the elements in this picture with the terms here on the left. Stop the film, and here comes the result. Here we have the circle center, here for example the radius, a diameter, Durchmesser. We have then the chord. This is a straight line from one point on the circle to another point on the circle. Then the second is any straight line that intersects with the circle. Den Kreis schneidet. We have the tangent which touches the circle. When we connect this point where the tangent touches the circle with the center, this line is then perpendicular to the tangent. There is also the passant, which is just a line that does not meet the circle. We have a sector, which is just a part of the circle starting from the center. The arc is the part of the circle line that belongs to the sector. And last but not least, we have also a segment, which is the area between a chord and the circle line. You all know the constant pi. It describes the ratio between the circumference of a circle and its diameter, and is approximately 3.14. Please note that I use the U for the circumference, the German Umfang. Solving this equation for u, we get the formula for the circumference of a circle as pi times d, which means pi times 2r, so 2 pi r. The formula for the area of the circle is pi r squared. These are two formulae that you have to know by heart. I know that students sometimes have problems to distinguish between the two of them. Well, here you have a squared. Well, when we have an area is with meter squared or centimeter squared, so that's why we have a squared in the area and no squared for the circumference, which is just the length. Note also that in both formulae there is a 2, a pi and an r. How do we obtain the formula for the area of the circle? Let's cut the circle in 4 quarter circles and let's then arrange them in a little bit a special way. The length that we get at the side of this figure is r here, and this length here is just half the length of the circumference since it consists of 2 quarter circles. So the length is pi r. Now let's split the circle into 16 equal segments and arrange them in a similar way like here, and we get this figure here. Again, this side of the figure is just length r, while this length here is just half the circumference since it consists of half the sectors. We can continue now and use even more sectors than 16, 1,000, a million or so. In the end, what we will get is just a rectangle with side lengths r and pi r. And so we get for the area of this rectangle, it is pi r squared. By construction, this area corresponds to the area of the circle. Now let us have a look at the sector and at the arc length. Well, the arc length is related to the length of the circumference and to the central angle alpha. I have just noted that we forgot to mention that before. This is the central angle alpha belonging to a sector. You see probably immediately that if this angle is 90 degrees, then this length here will be a quarter of the whole circle, because this covers then just a quarter of the circle. If this angle is 30 degrees, this means it's a 12th of the total 360 degrees. Well, then this part here will be a 12th of the total circle. So we find that the ratio between this arc length A and the circumference is the same as the ratio between this angle alpha and the full 360 degrees. Now let us look at the area of the sector. The ratio between this area and the area of the circle is again the same as the ratio between this angle alpha and the full 360 degrees, since this ratio tells us what part of the total circle area is covered by the sector here. We have said that L divided by U circle equals to alpha divided by 360 degrees, so multiplying by U circle we get, for the arc length, L equals alpha divided by 360 degrees times U circle. We said also that the area of a sector divided by the area of the circle corresponds to alpha divided by 360 degrees, and by multiplying with a circle we get the formula for the area of a sector, alpha divided by 360 degrees times the area of the circle. Let us rewrite this area of the sector as alpha divided by 360 degrees now times pi r squared, the area of the circle, and then transforming the pi r squared algebraically, we can write pi r times r and expand by 2 divided by 2. This here corresponds to the circumference u, so we get this expression here, and this corresponds to the arc length L, and so we find that the area of the sector corresponds to the length of the arc times the radius divided by 2. Compare that to the area of a triangle, length of the base times length of the altitude divided by 2. In that sense here the arc is the base and the radius is the altitude. So these are 3 additional formulae we use when talking about the circle. Now let us look at some examples. In example 1 we want to find the area of this segment here. We find it as the difference between the area of the sector and the area of the triangle. The triangle is an isosceles triangle, ein gleichschenkliges Dreieck, with base S here, and the leg Schenkel is R. The angle alpha here is 60 degrees. Now when we draw the altitude, here we get here half the angle of alpha, so 30 degrees. Here we have now a right angled triangle. We know this angle, we know this length here, it's the radius, so we can calculate this altitude. We can also calculate this length here, and using that we can calculate the area of the triangle. But we want to do it in this case in a different way. Let us use instead this altitude h star, which is the altitude to this leg of the triangle, to this r, and let us now first look at this triangle here. Well, h star is the opposite of this angle alpha, r is the hypotenuse, and hence we get sine of alpha is h star divided by r. Solving for h star, we multiply by r and we get h star is r times sine alpha. The area of this triangle can be now calculated as base times height divided by 2, so 1/2 times this radius times this h star. Inserting h star in here, we get this formula, and now inserting the values, we get 1/2 times 7 squared times sine of 60 degrees, which is approximately 21.21 square meters. Using the formula for the area of a sector, we get that the area of the sector is 60 degrees divided by 360 degrees times pi times 7 squared, which is approximately 25.66 square meters. And so we find that the area of the segment is approximately 4.45 meters squared. In example 2, we want to find the radius of a circle with circumference 1 meter, and then the question is by how much this radius is increased if the circumference is increased by 1 meter, so if the new circumference is 2 meters. We start with the formula for the circumference of a circle and solve it for r by dividing it by 2 pi. And we get r is equal to u divided by 2 pi. So r1 is u1 divided by 2 pi, so 1 divided by 2 pi, and we get that the radius of a circle with circumference 1 meter is approximately 16 centimeters. For the radius of the second circle with circumference 2 meters, we get approximately 32 centimeters. And so we find that the radius is increased by approximately 16 centimeters. In example 3, a rope is put around the equator, assuming that the Earth is a perfect sphere. Then the rope is enlarged by 1 meter, and we want to know how far now the rope is away from the surface of the Earth. This means we have to find the radius of the Earth and the radius of the new circle with the enlarged rope. And the difference between the two is then how far the rope is away from the surface of the Earth. Think about it for a moment and just intuitively guess how much will this distance be. And now try to solve the example by your own. Stop the film now. And here comes the result. The radius is calculated like before as the circumference divided by 2 pi, and we use for the circumference the 40 million meters. So we use it in meters and we get this result here. For the second circle with the enlarged rope, the circumference is 40,001 meter, so we get this radius here. And we get that the difference between these two radiuses is 16 centimeters. This is the same result like in example 2. Well, seriously, who of you really thought it would be so much? I'd assume that most of you would have guessed it would be less than a millimeter. That's what I did when I originally heard this task. Now let us show that this difference of 16 centimeters will always occur when we have some circle and we enlarge it by 1 meter. So I have circle 1 with the circumference u1, I add 1, and this is the circumference of my circle 2. Using the formula u equals 2 pi r, I get this equation. And to solve it for r2, I divide both sides by 2 pi. I get this expression here, and with some algebraic transformations, I get in the end that r2 is r1 plus 0.16 meters, so plus 16 centimeters.